Okay, we are back with some quick math. We are doing Euclidean Geometry. This is theorem 9. This is for the pure math. This is one that you do need to know how to do the proof of. So you need to know this off by heart. For the technical math, you need to know how it works. You don't need to be able to produce the proof. Okay, so I'm going to start by showing how the theorem works, and then I'm going to get into how we do the proof of it. So what I want you to see is that there's basically a triangle inside a circle, and then on one of the vertices, one of the corners of our triangle, there's a tangent. Okay, so I want you to see the tangent, and I want you to see the triangle. But if we do look a bit closer, then this line over here is a chord of your circle, or rather on your circle, yes, and there is a chord on the side as well, and there's a tangent. Okay, so this theorem is the tan-chord theorem because we look at the angle that is created between the tangent and the chord. So the tangent, this one over here, and this chord creates an angle that's over here. Okay, that chord that you have, when it subtends, it creates an angle that is over there. Okay, let's go back. Why did I just say? I said the tangent and the chord create an angle. I said the chord subtends an angle. So those two angles that I've mentioned there in green, they are equal to each other. Okay, similarly, the other side works the same. Let's put this in another color. So the tangent and this chord also creates an angle. So here's another angle that's formed, right? And then this chord also subtends another angle. So this angle is formed over there. Okay, basically, when you have, let's erase this. Right. So what I'm saying is, if you have a circle and you have a triangle inside a circle and you have a tangent, the angle that's over here is equal to that angle, the one opposite. And if you have the angle over here, it's equal to the one that is opposite. That's how the theorem works. Okay. Let's get into the proof. In order to do the proof, we start by doing a construction. And the construction that we're going to do is we're going to draw a diameter. So let's just zoom in a bit. I'm going to draw a diameter. So from here to here. And I am going to, we need all of these points named. So let's name this A, B, C. Let's call this straight line DE. And so all of those are probably given, and this construction line that I've drawn in, I'm going to name it FC. Okay, so I have that construction, and then I'm just going to close from F to A as well. Okay, closing from F to A. So this is what we've got. So that's the construction you do. Because of your construction, I want you to notice certain things. So I'm going to draw this in. This is just for our understanding. So we see that over here, this is a diameter, and our diameter subtends this angle. So we know that that angle is going to be a 90, right? Angles in a semicircle. We know that that's a 90 degree. Okay. We also know that this angle over here on this side is also 90 degrees. Now the reason for that, that is theorem 7, okay, but it tells us that if you have a radius and you have a tangent, the angle created between the radius and the tangent is 90 degrees, more of a definition, right? Okay, so we have a radius and a tangent, so that's 90. We have angles in a semicircle, so this is 90. So we have those two 90s, okay? Okay, in fact, let's maybe number some of these. So I have two angle A's that's created, this angle A and this angle A, and I have multiple angle C's created. Let's say this angle C and that angle C over there. Okay, maybe let's make arcs so we can see that I'm speaking about that part, and that is C1 and C2. This is A1 and this is A2. Okay, hopefully we can see the distinction between those. Okay, right, so the construction is only the orange stuff, and then you do obviously need to name those different A's and those different C's. Now let's get into the proof. Okay, so we are going to start by saying that angle A, let's say A1 and A2, right? A1 plus A2, that angle is equal to 90 degrees. Your reason for that, angle in a semicircle. right? And then you're going to tell me that C1 and 2, so let's say C1 and 2, C1 and 2 is equal to 90 as well, 90 degrees. A reason for that is tan perpendicular to radius. Okay, so we have those two 90s. The next thing that we see, let's go look back at the picture again. We see, let's put this in blue maybe. We see F and B subtend to create angle A1. We see F and B subtend to create C1. Okay, so what we are going to say is we are going to say that A1 is equal to C1. What is our reason for that? Angles in the same segment. Let's try that again. That word is segment. Angles in the same segment. Okay, that segment. So what we're saying is this. Let's go look back at the picture again. We are saying that this angle over here is equal to this angle over here, right? Of what that thing I've colored in. We've also said that this entire angle is 90. This entire angle is 90. So if the whole thing is 90 and this black colored in part that I've shaded there is equal to each other, this part that was in green that's left over have to equal to each other as well. Okay, so what we're going to say, therefore C2 is equal to A2, right? And that is our theorem. When you use this theorem, what you will write down is tan-chord theorem, right? You must write tan-chord and you must write the word theorem, tan-chord theorem. All right, so let's just look back at this again. What did we do? Okay, we said that there is a 90 over there because of tan perpendicular to radius. We said that there's a 90 over here because of angles in a semicircle. We said that this angle and this angle are equal to each other because FB subtends them, right? So it's angles in the same segment. And then therefore, this A2 has to equal to C2. That's our proof.